Hello everyone, it's nice to be here. It's quite an opportunity for an undergrad to talk about his research, so I want to thank the organizer for this. So what I'm going to talk about today is the use of convolutional neural networks, and YOLO especially, in the automatic detection in geophysics, and more especially geomagnetic. So what are we going to talk? So first of all, I will do a quick personal introduction. Then I will talk about the state of the art, and also a presentation of what the dataset I did use, the main characteristics, the classes, and of course, as a good Frenchman, I will then complain about the data. Then I will talk about my first approach, which is a simple CNN, custom-made for this task, the type of architecture, and the result we got. Then we will go on to the main course, which is YOLO, the methodology I used to train this network, and the result we obtained. Then we will conclude. Alright, so I'm a fourth-year engineering student at ECEA, which is a graduate school in Paris. I'm specializing in deep learning and machine learning and data science. And I'm currently working in sound event detection using deep learning at the SNCF in Le Mans. So state of the art. So there's already been work done in this area by actually people who are in this room. So Miss Kramer and I'm sorry, I'm going to destroy your name, Verschuur van der Vaart and all. So they've done mostly work on LiDAR data, but I've also seen work on ground penetrating radar. Most of this work has been done in the last few years, so this is quite a new area of research, and there's a lot of things going on at this moment. So presentation of the datasets. It is made of 109 magnetostatic surveys taken mainly from Marseille, France, and around the UK. There's two target classes that I've constructed: the anomaly class, which is contemporary ferromagnetic objects, and a feature class, which is a general entropic activity. So we can see actually two classes on this particular surveys, which is from Montagneusson, France. So on the top you have the structure class, and you see the little black dots, which is here, which will be the anomaly class. Moving on, so we have the structure class. Again, it is quite linear with smooth gradient variations, and the anomaly class is just pretty much a big blob because it comes from metal, and metal and magnetic doesn't quite do well together. Alright, so our problems now. Well, the small size of the dataset. As I've said, 109 surveys is not quite a lot for deep learning, which does come with a bit of a problem with overfitting. Also very varying resolution and size. Some of my images are a bit more than 1000 by 1000 pixels, and some of them are 7000 by 7000. So we have quite a large variation in size, so the objects sometimes, which are the same object, we could take up half of the image or just a few pixels. So we need something that is quite robust to scale transformations. And also, since we are working with magnetostatic surveys, it is extremely noisy, with noise spawning from all frequency domains, so all kind of filters you can try to use, they will not really work. And since we are, I am using survey coming from different providers, they all use some kind of different techniques to try and reduce the noise, sometimes they don't, with varying degrees of success, meaning not really much success. So, simple CNNs. So what did we do? Simple data annotation. So how could we fit a 7000 by 7000 pixel survey into a CNN? The answer is we don't. We segment them into 128 by 128 pixels square using the following method. So first off, we take the raw image, we manually select region containing an object, we call them region of interest, and then do an atomic segmentation, which is simply a sliding window of 128 by 128 with a stride of 48 pixels. We further on augment the data because we obtain about 20,000 segments from 500 zones, which is good. We augment those by introducing small variations using pre-processing, so shearing, zooming, and coloring. So the architecture, it's a very simple model, only about 8 layers, which takes, as I've said, a 128 by 128 feature vector as an input, 3 layers of 3x3 convolutions with a max pooling to reduce the dimensions, 2 layers of fully connected neurons, and a sigmoid output that outputs a 2x1 vector with class prediction. It was built with TensorFlow and Keras because we don't really like to program here, and trained on 30 epoch in about 1 hour using the ADAM optimizer on a GTX 1050 Ti. So validation loss is 0.39, which is not really interesting, but the validation accuracy, which is interesting, is above 90%. So we get some good results. So we can do an activation studies on the theater of Tarquimpol. So using a sliding window, we simply color the original image using the average of activation in the feature class. So this gives us a good idea of what kind of texture activates the network. And we get this, which is a bit dirty, but it will do. So we can see that the actual amphitheater is quite well covered, but we can also see that, well, this thing here, which was an anomaly, is also colored. So we have some bit of a trouble here. This is mainly due to the fact that we use a really small window size, so the network thinks that it is a structure when it is not. Alright, so YOLO v3 now. YOLO v3 is a really novel automated detection method. It was first introduced back in 2015, I believe, and the method, the v3, was introduced in 2018. So it allows boxing for the detected object, meaning that it can not only detect an object, but it can also produce a box around it and gives us the coordinates, which is perfect for our use. It uses a two-loss training system, one for the accuracy of the boxes and one for the accuracy of the class detection inside the boxes. It is also extremely fast, meaning that we can do real-time detection on objects, which is not interesting in our case, but that's fine. And also for variable size inputs. This has a caveats. Why? Because actually YOLO, what it does is that it reduces the size, it downscales the image to a fixed size. So we cannot fit the entire image. What we do is simply use large regions of the full-sized image. We limit the resolution to about 1000 by 1000, which is rather arbitrary. This region may contain multiple examples of a class, and this limits the information loss when YOLO downscales this image. So the data was manually annotated using label image, which is a free and libre tool. And we use a slightly modified YOLO v3 Tiny with only 2 class and grayscale inputs. We also use data augmentation, which is built in with YOLO. So this is rather comfortable. So training time about 12 hours on a GTX 1050 with 15K batches. 95% class accuracy, so we get about the same results as a simple CNN. And the average intersection of a union, which is a measure of how good the boxes are, is about 55%. The mean average precision is only 27%, which is not really good. So, some example. Well, on the left, a good example. It detects a feature, it's called feature, but it's a structure, rather well. We can see like a really nice box here, and also a really nice box here, and the anomaly is also really well detected. However, on the right, well, it has some troubles. It seems to manage to find the small features here on the bottom, but the rather huge feature here and here are not really well detected. Also, this thing not detected at all. This is mainly due to the fact that we have a really small data set, so it has some troubles to, well, learn on this. So let's conclude. Limitation and afterthoughts. Well, the small data set that we use prevents us from getting better accuracy on YOLO v3. This is a limitation that I cannot really do much about. Also, something that we should note is that the model that we use, like YOLO, but also faster SNN, I do not believe that they are well suited for this type of task, because they have some difficulties with relation with small or big objects when they are related to image size. And also, in our case, the precise annotation is often complicated. Geomagnetic surveys do not only show the object, but they also show the field of the objects. So good annotation is hard, and so precise inference of this annotation is really complicated. Also, something that I should note is that we are only detecting objects in a survey. This is more of a problem of computer vision rather than archaeology. So when we detect this object, we have no guarantee that there are real archaeological objects in the field. A survey is simply one of many views someone can have of the field. So when we do detect an object, we need to make sure that they are actually real, and this is something that is a different problem rather than object detection. So what's the main takeaway here is that deep learning allows us to make hands-off pretty much model creation. We simply give raw data to our model and let it learn, and hopefully we'll get some good results. Also, from an engineering standpoint, this is interesting. There's a short service to model timeline. From raw image to dataset to a working model, it took me about 2 months, which and most of the time was spent on annotating the dataset. Creating the model and training the model is rather short, so we could iterate really quickly on it and create something better. We also have an high accuracy and speed, even on noisy data and a small dataset. Further improvement. Well, we could always use more data, as it's always already been said, more data equals better model, and also more classes. But most importantly, I think we need to start working on the development of a model architecture that is actually suited to automatic detection in surveys, rather than just use something out of the box. It will need to be usable with extremely large image size, able to detect both large and very small objects, so robust, as I've said, to scale transformation, and maybe something that would be interesting is a simultaneous analysis of multiple data types, as it's already been said, maybe LiDAR, satellite images, ground radar, and whatnot. And of course, something that I would also like to see would be more open access data for better performance comparison, because it doesn't really make sense to compare models when it's not on the same datasets. Any questions?